Now we're going to see the proof of the punchline, the proof of this key property that made the quantum algorithm work to find the period of a simple periodic function. Okay, and again, what we needed was that when GT is this state, so a uniform superposition over all x, such that x mod s is equal to t, then when we take the Fourier transform of that state, what we get is a superposition over all y such that y mod n over s is equal to 0 of omega to the minus yt times ket y, and then normalized by this 1 over square root of s. Okay, so we did not need to use the exact form of this state. So the properties that were important for us were that all entries of Fn, all non-zero entries of the Fourier transform of GT have the same magnitude, and that the jth entry is non-zero if and only if j is equivalent to 0 mod n over s. Okay, and that these two properties held independent of what the value of t is. Okay, remember that we don't have any control in the algorithm over what t is, but these two properties hold no matter what t is, so that's fine. Okay, so let's see why the Fourier transform of GT is equal to this state. Okay, so we want to show that the Fourier transform of GT is equal to this state over here. So we start out just by taking the definition of GT and applying the Fourier transform to that. So that's equal to this sum here. So we have square root of s over n, sum over all x, such that x modulo s is equal to t, of the Fourier transform applied to ket x. Okay, now the Fourier transform applied to ket x, that is just the xth column of the Fourier transform. Okay, so now we plug that in here. So this is the xth column of the Fourier transform. It's just the sum over all y, omega to the minus x times y, ket y. And again, omega here is our primitive nth root of unity. It's just e to the 2 pi I divided by n. Okay, good. So now I'm just going to rewrite this sum slightly. So every x here is equal, so every x here mod s is equal to t. So that means that every x here is of the form k times s plus t for some k. Okay, so I'm just going to switch this sum to instead be over k. So k goes from 0 to n divided by s minus 1. And now we're writing x as k times s plus t. Okay, so this is just all the things that are equal to t modulo s. Okay, good. So this is just the, again, the sum that we had from the last slide. Now I'm going to interchange these sums. Okay, so I'm going to move the sum over k inside and move the sum over y to the outside. Okay, and now when I do that, then I can pull this term out, right? This term does not depend on k, right? So, I mean, here this omega to the minus ks plus t times y, that's omega to the minus ksy times omega to the minus ty. So this omega to the minus ty ket y term, it doesn't depend on k, so that's what I'm pulling out here. Okay, so I have this, and then the coefficient on ket y here is further multiplied by this sum here. Okay, so sum from k equals 0 to n divided by s minus 1, omega to the minus ksy. Okay, good. So now I can slightly rewrite this sum. So what is the sum of k times s as k ranges from 0 to n divided by s minus 1? Well, that's just a sum over all a such that a modulo s is equal to 0. Okay? And I just rewrite it in this way because this brings us to the key property of characters that we talked about last time. Okay, so we already know how to evaluate this sum. So if you remember from a previous lecture, we know that if omega, so what is this sum here, right? Sum over all a mod s is equal to 0, omega to the minus ay. Okay, so this sum, it depends on the value of omega to the minus y times s. If that is not equal to 1, then this sum is 0. Okay, otherwise every term in the sum is 1, so the sum is just going to be n over s. Okay, so when is omega to the minus ys equal to 1? Well, that's just going to hold if y is a multiple of n divided by s. Okay, so that's going to hold if y modulo n over s is equal to 0. Okay, so again, this condition is when omega to the minus ys will be equal to 1, right? And therefore, this sum here will be equal to n over s. Okay, otherwise, if y is not equal to 0 modulo n over s, then omega to the minus ys is not equal to 1, and therefore this sum is 0. And so there's the coefficient in front of such ket y's will be 0. Okay, so those terms go away. Okay, so what we're left with is a sum over y modulo n over s is equal to 0. We have this omega to the minus ty term here, and then this becomes n divided by s. So n divided by s times the square root of s over n gives us our factor of 1 over root s out here. Okay, so that's the proof of the punchline.